The committee for the IEEE Palouse section is always in need of volunteers for officers. So if any of you would like to get involved that way, please feel free. And if anybody's interested in helping to set up an IEEE Women in Engineering chapter, let us know and we'll get it started. Okay, now our speaker is Christian Légaré, I hope I'm pronouncing that correctly, and he holds a master's degree in electrical engineering from the University of Sherbrooke in Quebec, Canada. Throughout his 22 years in the telecom industry, he has been involved as an executive in large-scale organizations as well as startups, mainly in the engineering and R&D field. Mr. Légaré was in charge of an IP Internet Protocol certification program at the International Institute of Telecom in Montreal from 2000 to 2002. He is presently Executive VP and CTO with Micrium, home of the Microcost operating system. Realtime Kernel, looks like I got off script there. He is a frequent speaker at embedded systems conferences and silicon vendor dedicated conferences. And currently he's serving as Vice President of the IPSO Alliance Board of Directors. So that's the IP, Internet Protocol for Smart Objects, where he provides guidance on the embedded systems industry with the IPSO Alliance to advance the mutual goals of making the IoT a reality. And I'd like to see that for a project I'm working on. Okay, so I yield the microphone to Christian. Thank you.
Thank you, Charles. Thanks a lot. Okay, I'll try one thing. I'm French Canadian, so I have a bit of Latin blood, so I speak with my hands a lot. So standing behind a podium is not really my style. And as my father was a teacher, so I inherited from him a strong voice. So I'll try one thing, okay? I'll try to step aside at the podium and address to you without the microphone. If it doesn't work and you have difficulty hearing me, okay? Oh yes, I can also use it. Okay, cool. Then maybe I can also use it, but I'll try. Yeah, I can remove it.
But we're videotaping this.
Oh, you're videotaping me.
Yeah.
Oh. I forgot my tie. Okay, yeah. Questions with pleasure. Okay, at the end. Okay, so if you're videotaping, then I'll keep the microphone. Then it's gonna be better for the recording, for sure. Before we get into the subjects, I'll introduce a bit more of myself and Micrium so that you know my background and where I'm coming from and why I'm going to be talking about the Internet of Things, from a certain angle, a certain point of view, and I'll tell you a bit more, So I hope that when we're finished, you'll be able to have your own definition of what the Internet of Things is, because I think it's all kinds of things and it's everything and anything at the same time. So look at it. So yes, I'm the Executive VP and Chief Technology Officer at Micrium. Micrium is a company that was incorporated in 1999. Jean Labrosse is my business partner. We are two co-owners, so Micrium is still a private company, and we are two co-owners. My business partner, Jean Labrosse, wrote a real-time kernel more than 20 years ago, MicroCOS. Okay. Now we are at the third version of this real-time kernel. It's called MicroCOS 3. And MicroCOS 2, the one between the first MicroCOS in 1992 and now, has been used in the Mars Curiosity rover, is used today, and it's running today on Mars. It's in the Mars Curiosity rover, the laboratory that picks up the soil samples, analyze it, is run by MicroCOS. Okay, and when NASA used it, they didn't change one line of code. So I'm giving you that example just so that you understand that at Micrium, when we write software, we write C code, so firmware, real-time kernel, and all the other components around it, quality is fundamental for us. The way we write the software, the way we document it, the way we present it to the community, for us, the quality is primordial. Okay, it's really, really, really important. And when NASA used it and didn't change a single line of code, it tells you that I think we're achieving what we wanted to do. Now, around the real-time kernel, yes, we do have the other components. We do have a TCPIP stack, a USB host, USB device, a file system, a graphical user interface, and all these nice things, which makes it a full-fledged real-time operating system. So sometimes people refer to the kernel as the RTOS. But as a matter of fact, a kernel is just a kernel. An RTOS is a kernel with services around it. Linux is an operating system, but Linux has a kernel and Linux has other stuff around it. So Linux is an operating system. You don't refer to Linux only as an OS or only as a kernel. Well, when people talk in the embedded space, when people talk about a kernel, they often refer to it as an RTOS. But an RTOS is kernel plus all kinds of other stuff. So we are here today in 2014, and yes, you know, we take all this software that Micrium has been writing, you know, embedded real-time kernel, TCPIP Stack, and etc. And we've been selling this software, you know, since we incorporated the company in 1999. And we've been, you know, working with silicon vendors to say, hey, Mr. Silicon Vendor, you know, it's nice that you have this nice microprocessor, microcontroller, but your customers would benefit if you would put software with it so that they can have a complete solution, you know, when they're designing their product. And we've been doing that, as you can imagine now, for 15 years. And the silicon vendors were always telling us, yes, you know, but we don't have money, you know, and can you port the software yourself? And here's a $20 evaluation board. Can you put $50,000 of engineering time to put your software on it? And they don't do it once, you know, they do it multiple times because every silicon vendor, they have, you know, I don't know if you look at their product selector guide on any silicon vendor website, and you're going to see they have, you know, hundreds of parts. And of course, they have a new board, and they send it to us and say, put your software on it. Yeah, sure. So we've been trying to tell them, no, help us, you know, do that. And if you can subsidize, you know, we're going to do the porting of all the software, the Ethernet controller and the USB controller, driver, and all that stuff. And it's been always difficult. But for the last year, we said, okay, what is the Internet of Things? You know, what is it, and what are the companies building products need when they want to build a product to be IoT, to be an IoT device? Well, they need a real-time kernel, they need a TCPIP stack, they need a file system, USB host, blah, 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 a few protocols. Well, guess what? That's exactly the software we do. So what we did a year ago, we said, okay, you know all the software we're doing? We're going to put a big ribbon around it, and we're going to call it IoT. So it's IoT software. You can't imagine how the doors suddenly open. Boom. Oh, yeah, we need you. Come here. You know, we're not selling anything different. It's exactly the same damn software, exactly the same one. But because we're putting the IoT label on it, suddenly it triggers the imagination. I've been visiting, you know, dozens of companies in the last 12 months, maybe close to 100. Every companies that I visited, every single one has an IoT strategy. Either they name someone, an engineer in charge of IoT, or they created a division, or they created even a VP of IoT within the organization. Everybody has an idea that they'd like to do that. Do they know how to do it? No, they don't. But they say, oh, it's cool, we should do it. The other thing about IoT that is very important is that, you know, I graduated in 79, my electrical engineering degree, and 82, my master degree. And at that time, it was the boom of the electronic industry. Silicon Valley was a place where everything could happen. You know, there was Steve Jobs in his garage, and Hewlett and Packard, and all these, you know, all these companies inventing stuff, etc. It was booming. At this time, the embedded system conferences, when one of the embedded system conferences in the 80s, you know, were running, there was you know, cookies at the coffee breaks, and there was fountains of chocolate, you know, liquid chocolate. It was the era of the electronic. Now, the microcontrollers and the microprocessors now are starting to be commoditized. It's a commodity. Today, you can get a 32-bit Cortex-M for less than 50 cents. Okay? Imagine that, a 32-bit processor for less than 50 cents. It's really being commoditized. But now, with what we're going to get into it, what we call IoT, the same energy, the same dynamic that existed in the 80s around the electronic industry is coming back now with a new team, which is now software. Because if hardware is a commodity, what makes IoT so exciting? It is the connectivity, and connectivity is driven by the software, the communication stacks and what you do with it, etc. Okay? So we are really just at the beginning. And this is why I say catching the IoT wave is just like a surfer. Okay? This wave is just starting. If we can just start and know how to get on it, we'll be able to surf for the next, 10, 15, 20 years. Because this is where the industry is going. It's really exciting. Even if, I was 23, 24 years old in 82, 83, and now it was fun as a young engineer to work in the electronic industry. Today, in 2014, with this, I feel rejuvenating. I feel re-energized. Okay, it's like, wow, we're gonna surf another wave like the one we knew in 40 years ago, which is fantastic. Okay. And of course, there's one thing you should not do. If you have a Twitter account, don't try to follow all the tweets that starts with IoT or Ash IoT or etc. because you're going to be inundated. There's so much information right now on IoT that we need to find ways to sort through all this information, okay? If you webs and newsletters and e-magazines and of course Twitters and LinkedIn and all the social medias, etc. Trying to sift through all that, it's a lot of work. Okay, so I gave you a little bit of who I am, where I'm coming from, and where I'm gonna take this presentation now. So you'll see that, of course, I have an embedded system point of view. I have an electronic component device point of view. But the IoT is more than that. But you'll see why I'll spend more time on some of the topics that I know, but I'll start to scratch the surface of other elements that make this whole thing possible. Okay. Also, the other thing, at any point in time, I know we've reserved time at the end of this presentation, etc., for questions. But if you have questions, even in the middle, okay, please don't hesitate. Stop, raise your hand, and I'll be able to address. Okay, and Chuck has a additional microphone that we'll be able to use for questions. All right, don't hesitate. Okay, this slide is my view of the IoT. Okay, and why do I say my view of the IoT? Because the IoT is what you're going to make of it. Okay? The thing with IoT is that, I don't know if some of you, when you read articles, etc., Gartner came up with a curve they call the disillusionment curve. It starts, with any technology goes up, and then there's a hype, and then there's a disillusionment, and then before it plateaus. Okay? Well, IoT is also following that kind of curve. So we talk a lot about it, and then people starting to say, yeah, come on, it's too difficult, it's going to be difficult, and then we're about, in that phase. So there's so many things being said about the IoT that, a good portion of it is true, and the other portion is you need to figure out if it's applicable to you or not. Now, sometimes people refer to it also as M2M, machine to machine, IoT or CPS. Cyber physical systems. This is something that the federal government in Washington, D.C. has been working on, and it's all the same thing, okay? And it's only what is important for you in all these things. The thing you can say that M2M, machine to machine, is a subset of the IoT. Why? Because in machine to machine, the internet may not be involved. Okay, when you have a machine talking to another machine, it can be on a proprietary network. or it can be on some IP network, but it can be private. It doesn't have to be the public internet. Okay? So you can view M2M as a subset of IoT if you want. But IoT is now the things being interconnected, the things, the devices, the electronic products you guys are designing, working on, maintaining, supporting, and all that stuff. So the way I represent the definition or the structure here is that on the left, I have the electronic the device, okay, the thing itself. Now the thing has sensors or actuators, so that's the symbol I'm using for sensor actuators, and then some type of processing, and then communication. And I'll explode this box a little bit more later. Now, this device, and what makes the IoT is only the connectivity, okay? Because these devices are connected, now you can say it is the Internet of Things. Now, the Internet, of course, suppose that you're gonna be using the Internet protocol itself, okay? From these devices, you need to extract the data, and then this is why the second step is a local network. The local network is whatever is used in the environment. It can be IP-based, IP in the sense of Internet protocol, or not, okay? And there's tons of local area network that are not IP-based. But, and that's one of the things I'm going to be also addressing to you, is that I'm a strong promoter of using the Internet protocol from end to end. And I'll tell you why a bit later. Now, from these local networks, if these local networks are not IP capable, then we need to have a gateway somewhere that will take this local proprietary or non-IP communication protocol and move it to IP, okay? What example can I give you? Okay, you know, in the past, thermostat used to be just devices that were controlling the temperature in a room or in a set of room, etc. Since Nest came, and then suddenly Nest made the thermostat a connected device over Wi-Fi and then of course IP, etc. So Nest is a good example of you take the thing you're working on today and you make it connected, and suddenly when making that thing, that device, connectable, suddenly it adds value to it. There's more you can do with it. There's additional things that you can sell or service or bring value added to your company, your customers, and the whole society. Okay, and I'm going to get to this also a bit later. So this is an example. You can have a device that was there a long time ago and that always existed, but then suddenly because you add connectivity, then it adds capability. So you move gateway, the internet. In the internet, we're going to look at the protocols. We as humans have been using the internet now for quite some time. We have HTTP and we have SMTP for emails, and we have JSON and jQuery and all kinds of XML and HTML and all kinds of technologies. So for humans, we have hundreds of protocols that allows us to surf the internet, browse the internet, find the information we want, on a daily basis and for our work, etc. Now, can the things use the same protocols? Maybe, maybe not. And we'll take a look at it. Now, this is why, so 1, 2, 3. Now, the fourth component in my definition of the IoT is the availability of a back-end service, or often referred to as the cloud, okay? So the cloud is only the sum of machines that we use daily. So as humans, when we go on a web server, etc., it's one of these machines on the cloud, on the public internet, which talks to other servers, etc. Now for IoT devices, we can do something similar. We can have back-end services. Now, like the Nest thermostat connects to a server somewhere at Nest, and Nest has the knowledge of what you're doing with your thermostat, and when you're using it, when you're not using it, and if it's in good health and whatever, and pushes firmware update to the thermostat, etc. Now, I'm using the Nest thermostat, but it can be a car, okay, whatever. whatever you want as the device. Now, the backend services, we're going to touch it also. So I'd like to go over these 4 major components of my definition of the IoT. And what you need to see is that how does it apply to your environment? It's like in any business, you know, you're in the electronic industry, you may know someone in the pharmaceutical industry. The person you know in the pharmaceutical industry may have processes and systems, and if you talk to that person, you're going to find that there may be good ideas in that field that could be applied to your field. Okay? And they're the same thing here. It's because there's technologies, there's hardware, there's software in all kinds of area. Look at it, because it means that maybe there's something that you could learn and use in your own products. Okay, so again, you know, the connected devices, what is it? It is the communication stack, it is the application, and then at the application, here we may want to touch also programming languages, okay? Because it may have an effect. And the requirements, the hardware resources, and I can also suggest that the hardware resources mainly for the software itself, especially memory. Okay? Again, this is just another view of the connectivity and at the various location. Okay, so a personal area network is something that is, you know, around your body. Okay, so the Fitbits, the watch, the smartwatches, that type of stuff, it is in a personal area range. Okay, the local area network, it's your home network, it's your office network, it's something that is local. The metropolitan area network, something that covers a city, for example, and of course a wide area network, then something that spans the whole the world. Okay, and then in these different locations, then there's different technologies that are applicable. Some that are better than other. Some that I know, some that I don't know. So there's some I can talk to you about, and then some that you are probably using in your daily activities that, you know, I've never myself worked with or experimented. Okay. The other thing I wanted to Chuck mentioned that I was the VP of the IPSO Alliance. So IPSO stands for IP, Internet Protocol, for Smart Objects. Otherwise, a thing in the device, a device in the Internet of Things that is using IP technology to bring some intelligence to it. Now, IPSO Alliance was formed 6 years ago with the mandate to promote the use of IP. So why should we use the Internet Protocol when we're developing a connected device? Okay. This year, in 2013, the IPSO will change mandate because we believe now that the majority of the manufacturer, the system developers, hardware engineers, software engineers, are now understanding that if you want to do an Internet of Things, it's yes, you need IP. You need IP technologies. You need the IP stack of protocols to be able to do that. So the mandate will change in 2014 into how to use IP. Because even if we understand that we need to use the Internet Protocol, which one? There's thousands of protocols doing all kind of stuff. But the idea here is that don't reinvent the wheel. Someone in the IETF, in the Internet Engineering Task Force, or in the IEEE, defined a standard, published it, had it approved, drafted, approved, and published that addresses your problem, or one of your problems. So try not to reinvent the wheel. Try to find the existing standards that exist and apply it to your problem. And that's what the IPSO is going to do starting this year. We're going to start publishing reference architectures. We're going to publishing definitions for smart objects, architectures, reference models, etc., so that you can, you know, we can tell to the rest of the developers and the engineers, this is an example of how it could be done, and with the existing technologies and standard. Why are standards important? And I'll repeat it multiple times today, is because when you're using standards, you're making your products interoperable. Your product will be able to work with products from someone else, and that's a huge value. If every company tries to build a silo, then yes, it's going to work for a while, but it's going to remain a silo. If we can have the products starts to operate together by using common technologies, then it's the whole value of the whole society that will increase. That's one of the big value behind using the internet protocols in this case. IEEE, your own organization, also just approved a project, you know, the P2413, the project authorization request has been granted, and this week, you know, at the end of this week, the first working group meeting will happen in Munich, Germany. So this is also interesting, and this is why with the IPSO Alliance, we're going to work with IEEE also to see what's happening in that working group, so that we can, you know, try to come together to an agreement on how what it should be used. So this came out from an article, and I gave Chuck this PowerPoint presentation, and this is the link to the article. So when you're going to get it from, if you want to get it from Chuck, you'll be able to go and take a look at it. So the title was IEEE steps in to sort out the Internet of Things confusion. Okay, so members of IEEE in other chapters around the world will be working on this, and I think that's great news that everybody recognizes it. Okay, now this is my definition of IoT. I told you so far, etc. But there's tons of things happening right now in the Internet of Things, and people are starting to, you know, segregate or separate the type of devices that are being developed. So some of them are going to put them into the industrial IoT portion and other in human IoT portion. Human IoT are more of the consumer type products, okay? Now, Gartner and Cisco and ARM have all, you know, announced that by 2020 there will be 50 billion devices connected. Well, out of these 50 billion devices, 8 billion, about 16%, will be in the human part, the consumer part. The smartphones, the tablets, the smartwatches, the Tidbits, the Nest thermostat, you know, the things we as consumer will see and use. This is the visible part of the IoT. The invisible part, the other 42 billion devices, are in the industrial section. This is the things you and I are working on, but that the average consumer won't see. Why? Because it's going to be in a ceiling, in a wall, in a plant somewhere, in a water filtration plant, something. It's going to be hidden from the general public. But this is, you know, over 40 billion devices in that field. And the main differences between the two is that's it. You know, in industrial IoT, the product life cycle should be, it has to run until it's going to die, or until we're going to make it obsolete because we're going to come up with a better idea. In the human IoT, well, you look at what Samsung and Apple and all these consumer electronic goods manufacturers do. Well, you have a phone now, in 6 months you're going to have a new one, and you're going to have a smartwatch, and you're going to have something else, and so they're even pushing, they're making their products obsolete themselves. So the life cycle in the human IoT is a lot faster. Availability also in industrial IoT, you know, we want. Yes, you have a question?
So, one of the current. There yet?
Is there a switch on the? Okay, Jared.
One of the current. It's on. Okay. Do you have a switch here? Let's try that. Oh.
Not better.
Okay.
Let's try this one if you want everyone to.
One of the current issues we run into is that the components are being driven by the smartphones and things that are just obsolete so quickly. Do you see that changing with the Internet of Things? Like components being longer lasting, that kind of drive?
What is a component for you?
Integrated circuit, for instance, or even resistors, capacitors. Capacitors they'll make just to last only so long.
No, I think both will exist. It's like military grade. Whoops, sorry, I'm going to fall behind. Military grade components versus commercial components. So, yes, components will exist so that it's gonna die in 6 months. It's planned obsolescence, okay? But for industrial grade product, when we need an availability of 5 nines or 4 or 5 nines, we need components that are, and these components will still exist. Of course, the one used in the consumer industry, they're cheap because we know we're going to replace it. Of course, the one in the industrial grades or military grade, yes, they're more expensive. Okay, and that's the big difference. And this is what you need, and this is what the silicon vendors and the component manufacturers start to realize, is that the Human IoT is about 16% of the market. So they can't align their product strategy on 16%. They have to align it on the 84%. Okay, and this is where you're going to see ARM, the IP design house of the majority of the microcontroller that we're using today, the Cortex-M and the Cortex-A, etc., which almost every silicon vendor now has a Cortex-M or multiple Cortex-M, Cortex-A based. So ARM is investing heavily into sensors and that type of stuff, because they see this is where the volume will be. So there will still be a volume for quality components for industrial devices, thing devices. Okay, but this is the two trends that if you want to start to grab things together and make your own mental image of what it is, you can start to do this. But of course, it's not limited to this, but it's a good segregation. Okay, so the device itself, what is the device, the electronic product you're working on? So we need to look at what variables are we measuring or control. How do we want to have an access or an action on some variable? So the interface to the analog world. At which frequency, how often do we need to take the measurement or take the control on that device, because it has an effect on the choice of the processor and the performance of the whole system. Now, if we have this data, this sensor data that we want to take out, or this control that we want to have on this device, how do we do it? Do we do it over a wired communication protocol or wireless communication protocol? And there's tons of them. Okay, and then in the wireless, we have the 802.15.4 and the Bluetooth and the Wi-Fi and ISA 100 and wireless HART, and well, there's tons of them. Wired, and we have Profinet and DeviceNet and BACnet and Ethernet and Ether IP and EtherCAT and, well, name it, Modbus, and okay, so many of these wired protocols. So which one? Sensing, processing, networking. Okay, sensing, we know, we've been doing that for a long time. Processing, we know what the processors we have available. What is new normally for these devices, a lot of them, is the networking capability. Communication stacks are fairly heavy protocol stacks, software, and the memory requirements to run these protocols are not negligible. The other thing in your device is that you need to see if you can have a device firmware upgrade, and here I'll even add one more adjective: secure device firmware upgrade. Now, we're talking about over the air, firmware upgrade over the air. So what does it mean? Okay, so if you're designing a device and your marketing people will always do the same thing, they're going to push you to get the device out ASAP, right? They'll do that, right? Okay, and they'll say, it's just software, we'll fix it later, right? They all do that. Okay, so so you can say, yeah, we're going to do it, but if we do it, we need to have a secure device firmware upgrade mechanism to our device. So because you want to get the product out, you want to get the market, you want to get the large part of the pie in your own industry, it's okay. Being first to market is always good, but sometimes your product may lack a feature or two, or things may have a bug even. Okay, and making sure that you can fix that remotely is a tremendous asset. To do that, of course, your bootloader will need probably more RAM, more code, more space for code, so flash requirements, and of course the networking capability to do that. Which, if it's connected, it's okay, but then the connection may need to be secured, for example. Okay, because you don't want everybody to be able to update your firmware. Okay. So the type of things I'm going to go. So again, this is going again over IoT for consumer versus industrial. So local networks. These are just a list of some of the wired communication protocol, and on the right some of the wireless communication protocol. And I'm sure this is not exhaustive. Okay, you probably will find some of the things that you work on, today. Okay, and maybe there's some in there that you use that I didn't list, but this is about it. Now, the thing is that not all of these wired or wireless protocol are IP capable. But if you want to use one of these, wired or wireless, I strongly suggest that you start with a protocol that is IP capable. No, in the wired category, of course, Ethernet. Yes, it's easy. It's an obvious choice. In the wireless part, Wi-Fi is an obvious choice. Zigbee IP is an obvious choice also because it can carry an IP packet. Now the other ones, yeah, probably not. But it doesn't mean that because it is not able to carry an IP packet that you should not use it. If it's the right protocol to use for your application, it's fine. The only thing you'll need to do is to make sure that there will be a gateway somewhere. A gateway between the non-IP world and being able to move to the IP world. This is what the telecom operators or the alarm company are doing, okay? When they're putting, for example, ADT, they base some of their infrared sensors and contact sensors, etc., using Z-Wave technology. Z-Wave is not IP capable. But what ADT does somewhere in the house, there's a gateway between Z-Wave and IP. And then you can take this and move it to your to the ADT account and do that. So that's an example. And the telecom operators, the public utility, the electric company, the water company, the gas company, etc. They all do something. So they have devices. They may not be IP, but somewhere, either in the house, in the meter, etc. There's a gateway. Okay. Now for the design of the thing itself. What we see in general is it's either that. It's either a dual processor system. Why? Because the first one, the top one, is either a 8 or 16-bit processor. Why? Because it can be really low power. And in sensors, it is important. In sensors, what we want the sensors to be able to run for a long time, especially if it is in a remote location, and even being able to work off batteries for years, okay? And this is why a low power processor is often the one used to do the sensors and actuators. But if you need to move data out of the sensor, then you need something to run a protocol stack. And in this case, this is why a second processor is often required. And especially if you move into the Wi-Fi and the Bluetooth and the Ethernet, and that's why a 32-bit processor in this case is required. And I'll give you other design alternatives to that in your selection. The other way to design your hardware for the device itself can be also a single processor. But if it's a single processor in this case, then you have no choice. It has to be a 32-bit processor. But again, remember I told you can get a Cortex-M today for less than 50 cents. Now, Cortex-M is still a fairly low power. It's not as low power as a PIC-12 or as a AVR or that type of, or Atmega 256, that type of stuff. But I can tell you that ARM is working really, really strong to come up with 32-bit processors that will consume as less power as a 8 or 16-bit processor. But today, if you want to run it's a communication stack, the issue here, okay? And if you need to do that, that's why you need that type of processor. Now, just to give you an idea also on some of the wireless communication and the size of the stacks, okay? Zigbee, a coordinator router in the Zigbee network is about, above 100 kilobytes of code in code size and 7 kilobyte in RAM. The end device itself is also around 100 kilobyte and 3.8 kilobyte in RAM. The 6LoWPAN, which is IPv6, for low power personal area network, then it's also, in the range of 50 to 100 kilobytes. and of course RAMs again in kilobytes for the buffers. Now 8-bit, 16-bit processor normally don't have that much code space and RAM space, and that's the issue. This is why you can't run it on the 8-bit, 16-bit. It has to run off the 8-bit, 16-bit, or unless you add external memory to your 8-bit, 16-bit, but then your stack will run probably fairly slow also. Okay. This is why performance versus power versus performance. This is why 8, 16 bits, if you do the sensing only, it's okay. The thing is that's why the model with the dual processor design is good, because it doesn't mean that you need to power on the communication part all the time. You just need to power it on when there's something to transmit or something to receive. Okay, and this is why you can still design a low power system with a dual processor approach. Okay. Now the thing is that look at the last bullet, and this is what I was telling you. ARM is working on something that they call close to threshold voltage CMOS, meaning close to 1.3, 1.4 volt. Okay, and that's going to be the switching, and of course it's going to run now in the kilohertz. So we're used to processors with megahertz. Now these processors will run in the kilohertz, but you can see that how very few power this type of processor architecture will do. So for a sensor, that would be a perfect design choice. But it's coming. ARM is testing it now with Silicon Foundries, making sure that the process is applicable. This is a table, showing you from different silicon manufacturer. These are 8, 16-bit processor. And what I want to show you is the two right column, okay? The ROM size and the RAM size. And this is why. When you look at the size of memory for code and RAM for all the variables and all the things in your device, there's not much room for a communication stack in there. And this is why. This is why it's difficult to run a communication stack on a small processor. Now, this is also why there's an explosion in the 32-bit processor architecture. And this is a slide coming from ARM from their 2013 annual report. Okay, so they're forecasting all the billions of devices and how many will be 32-bit, and it's only because of the connectivity requirement. Okay. Now, if you're designing a wireless sensor network, okay, using Zigbee or 6LoWPAN or ISA100 or wireless HART or that type of stuff, okay. Now that's what we call in a wireless sensor network. We call these nodes the end nodes, and this is what the things you need to run on these nodes, okay. A real-time kernel, of course, I'm gonna talk from my own parish, because at Micrium we sell a real-time kernel. But as soon as you get to communication stacks, other things than your application, 8, 16-bit, we are used to program these 8, 16-bit processors as a single thread application, as a super loop, okay? We're used to do that because it works well. Normally, you see the size of the application we can fit in the code space that we have. It's manageable. It's humanly manageable. But as soon as you start to get larger application and a lot more code, including networking stack, then it becomes a lot difficult. And this is why using a real-time kernel will help you in your design. The real-time kernel, even if you don't need the real-time capability of the kernel, the architecture the real-time kernel imposes on you is the following. You need to define tasks that are doing specific action. We can split the development amongst the team we have here. You can do task 1, you can do task 3, you can do task 4, I can do task 5. And then, because the kernel provides you the inter-task communication and synchronization, when we're going to put our tasks together, okay, there's a high probability that everything will work. Also, if you ever need to go back to your design, finding a problem or adding a feature, because your software architecture is already designed in a task doing the keyboard reading, a task doing the graphical user interface, a task doing the sensor, a task doing the A to D, a task doing the whatever. Then it's a lot easier to find where the problem is or add a feature. Because, of course, your marketing folks will come say, hey, that would be good if we could add this. Now, if you had designed your whole thing as a super loop, as a single-threaded, where do you put the new feature in the single-threaded? You have to tear it apart, find a way to insert it, and you're screwing up your whole timing in your super loop. With a real-time kernel, you can add a task, modify a task, and you'll be able to keep your timing, etc. So it's not because you're going to need the real-time capability of the kernel, but the kernel will force you to do a good software architecture. And it's going to be easier in development, easier also in maintenance and enhancement of your product. Now, mainly on these small devices, we're used to program in C, okay? C, sometimes C++, okay? But again, I think from the UBM surveys, years after years after years, United Business Media, C is still the predominant programming language for firmware and embedded software. Now, does it mean that we cannot run Java? And I'll tell you why I'm mentioning Java here especially. It is estimated that there is 450,000 embedded software engineers in the world. Now, if we want to develop the IoT, the 50 billion devices connected to cloud services, etc., we're going to run out of steam with 450,000 embedded software engineers. So how can we develop applications for these devices that can be loaded dynamically and unloaded dynamically also, and being able to design a application store similar to the Android store, similar to the App Store, Apple App Store, etc. It's by using another technology, Java. Why? Because we estimate there's 9 million Java programmers in the world. Okay, so there's a lot more probability that we'll be able to develop applications in Java. Now, the thing is that Java doesn't run on a 8-bit, 16-bit, or a Cortex-M. It's too large. If you take Java from Oracle. But there are solutions, okay? And I have one for you. Okay, and this is a diagram showing you, the architecture, the software architecture for a one processor node. So all the things. So the orange bottom part is the hardware. The radio, if it's Ethernet or Bluetooth or Wi-Fi, etc. The stacks themselves, the Bluetooth stacks, the 6-LoWPAN stack, etc. And then the application software, the firmware. One thing I didn't mention: power management. Okay. So if we want to design low power stuff, we need to also have the capability to do power management. Now, the problem with power management is that it's different from vendor to vendor. It's different from processor to processors. I don't know if you ever looked into, let's take an example, TI OMAP technical reference manual. You know how many pages there is in this reference manual about power management? 400 pages. 400 pages to do power management, okay? So this is why. Now, this is something also the industry needs to work on, trying to have a unified mean of doing power management so that when we have a processor from Atmel or from NXP or from ST or from TI or Freescale, then at least, all the routines we wrote to do power management can be reusable, okay? So I'm not against rewriting stuff, but there's stuff that it's okay to rewrite because it's not that complex, and other stuff that are a lot more complex. Power management is one that is complex. Just for fun, how many of you have written a UART driver in your career? How many? Once. Once in your career, once. Okay. How many have written it twice? Never? You've written it once only? I think I've written a UART driver at least 10 times because, one for an NXP part and one from an Atmel part, etc. So that's UART, not too bad, but power management, it's very, very difficult. This is also the software architecture for a consumer IoT. Why? And here, this is why I put the Java virtual machine in there. And this is where, because a consumer device will require software uploads or upgrades or services, okay? At Micrium, we've been working with telecom operators that are putting gateways into houses. And the telecom operators, they're selling services. And one way to do that is to use Java, because this consumer subscribes to a service, it's loaded to its box, and he pays X dollar a month. He unsubscribed, the service is offloaded from the box, and here's his bill at the end of the month is reduced. So that's one way to do it. Below the Java virtual machine, I have the virtual market specific protocol, because this is also a topic that is not simple, because every vertical market, medical, consumer, smart grid, etc., they have their own protocol. And I've put some of the ones at the bottom right of the thing. All-Seen is something that was designed by Qualcomm, that has been now being released in the industry. Qualcomm called it All-Join, and now it's called the All-Seen Alliance, and it is a protocol for consumer devices. Home Club, Home Grid, there's two competing protocols for smart grid, or using the home power network to move data. Continuum Alliance is something in the medical field, okay, and so on and so on. So you see, for a consumer device, there's more software that can be involved, and this is why in these type of devices normally we're going to see a Cortex M3, M4, and even a Cortex A because of the software requirements on it. Now, in a wireless sensor network, yes, we have the sensors, but then we need what we call an edge node, because if your wireless technology is not IP capable, you need to be able to move to IP somewhere. And you do that using a gateway. And in this case, this is why you have some type of communication stack on the left side and the IP communication stacks on the right side. Okay. In this case, the software will require more performance from the hardware. Java is also an option. Again, as I told you, some of the examples I gave you about the telecom carriers offering these gateways in the houses. Comcast is also coming up with a similar model here in North America. Okay. Okay, why Java? And I told you why. And the middle paragraph here is the Oracle Java embedded ME memory size. And as you can see from these numbers, well, it's fairly big for the majority of the microcontrollers and microprocessors. So it's fairly large for Cortex M. For Cortex A, yeah, it would work pretty well. But for Cortex M, it's tough. But at Micrium, we're working with a French company called IS2T, and they have a Java virtual machines that runs within 40 kilobytes of code. Okay, so there are solutions for Cortex M if you want to use Java in your Cortex M. Now, we're moving slowly now from the hardware, the local area network. Now we're getting into IP. This is the OSI 7-layer reference model for communication stacks applied to IP, or as we call it all the time, the TCPIP stack. Now, unfortunately, it's called the TCPIP stack, but it's not only because it uses TCP and IP. There's a lot more protocols into that stack than TCP and IP alone. But the thing for you, or for us, the hardware the engineers or the embedded software engineers, is that implementing a TCP/IP stack into an electronic product is a lot more difficult than doing it on a PC. Now, if you ever programmed networking application in Windows or in Linux, we just open the socket, send on the socket, receive on the socket, close the socket, right? Easy. Now, if you want to do that on an embedded system, unfortunately, you need to think of your hardware first. So when you do it on a laptop, a PC, etc., normally as a software engineer, we go top down. Now on an embedded system, we need to go bottom up. We need to start by the Ethernet controller itself. Because unfortunately, not all Ethernet controllers are born equal. Some Ethernet controllers have DMA, some don't. Some have memory, local memory, some don't, okay? So the performance of the Ethernet controller will vary greatly. So the driver, so this is why when you're implementing TCP/IP or embedding TCP/IP in a product, you need to start bottom up. You need to start by your Ethernet controller and the driver. Once you have it done, then yes, the rest of the stack is the same, and then you can use a socket, open, send, close, receive, okay? But basically, you need really to start by having a very good Ethernet controller. The size of a TCP/IP stack. When I was telling you, how much memory, so I gave you ZigBee and 6LoWPAN, and this is an example here, for TCP/IP stack, very typical, IPv4 only, IPv6, or IPv4 and IPv6. Now, why am I introducing, IPv6? Because it has to happen. It's not here yet, but it has to happen. The thing is that in North America, in the IPv4, the 32-bit IP address that we have, from the address 0.0.0.0 up to the highest address, 255.255.255.255, 70% of that address range was assigned to North America. Well, I'm Canadian, you're American, so I'm including Canada with United States, because yes, out of this 70%, was assigned to North America. 30% was assigned to the rest of the world. Europe, China, India, and Eastern Europe, Russia, etc. In the other countries, like China and Europe, and they're using IPv6 already, because they had no choice. They don't have enough IPv4 addresses. In North America, we were very lucky to get 70% of the IPv4 address space. But right now, it is limiting our industry. It is limiting our capability to come up with better products or more innovative products. Why? Because IPv6 allows for global end-to-end public addresses, peer-to-peer communication globally. Okay? So for an IoT device, if an IoT device can have a public IP address, then it's a nice feature. It's a good feature to have. Now, with IPv4, then this device has to be behind a router and a firewall, and we have to have network address translation, traversal, and then all these questions. Okay, but just the stack itself in North America, if we just want to work with IPv4, you already see the size. Okay, now I put TCP enabled and TCP disabled. Why? Because not all products require TCP. TCP is a protocol that does acknowledgement, meaning that when a TCP packet is sent, it has to be acknowledged by the receiving station before this packet is discarded by the transmitter. And TCP does also flow control. So when a station sends TCP packets to the receiving station will say, I can receive, stop, slow down because, stop. I have no more resources. I can't take these packets anymore. So TCP is good for that. This is why TCP is used for HTTP, the web, is used for email and all that stuff. But if your product is whatever IoT devices, maybe TCP is not required. UDP may be good enough. Okay? If your product is sending data, once a minute or something like that, and it's just sending a few hundred bytes, UDP will do the trick. Okay? You may have to do at the receiving station, put a bit more of the control, but it can do the trick. But you see, you're going to save a lot of code space if you can live without TCP in your embedded product. Okay? But code size, I wanted to make sure that you saw that how big TCP, and this is only TCP IP. Okay, it doesn't. If you want to add application protocols on top of it, like HTTP and MQTT and CoAP and web server and etc. Well, it's gonna add up to the code size. All right. And that was a configuration that was used to produce the numbers you just saw. Okay. Okay. The wireless LANs. Okay. One thing I wanted to here to show you is the Wi-Fi stack. If you're using Wi-Fi, now we just saw TCP. Wi-Fi itself adds as much code and RAM usage than TCP itself. So if your system, if you want to implement Wi-Fi in your system, then you need also to think about the code size and the RAM size you're going to use, you're going to need for running Wi-Fi. Also, Wi-Fi comes with certain features. You can use Wi-Fi as a station, so it's just a device. You can use it as a AP, an access point, okay, meaning that your device can also add as an access point for other devices that want to connect to it. And there's also a feature in Wi-Fi called Wi-Fi Direct. Anybody here heard about what Wi-Fi Direct is? You don't? Okay. Wi-Fi Direct is a feature in Wi-Fi where one device, that is Wi-Fi, can talk to another device without a router between the two. It's called Wi-Fi Direct. Pretty cool, because if you're developing a device and you want to put it in a wall, a ceiling somewhere, and you want that device to connect to your Wi-Fi network, how do you do it? You need to give it an SSID and the password, etc. So, but if you don't have access because it's a black box and it's in the wall, but it's Wi-Fi enabled, well, if you come close to the device with another device that is Wi-Fi enabled, like a smartphone, a tablet, you'll be able to do Wi-Fi Direct, and you'll be able to tell that device, here's the SSID you need to use, here's the password, go connect to the network. Pretty cool. So suddenly you just found a way to commission a device quickly, okay, and efficiently. Now, the thing I want to get here is this. With Wi-Fi, there's many vendors of Wi-Fi modules that are available today. You can buy a little module that runs a TCPIP stack, runs a Wi-Fi stack, is FCC certified, comes with a little antenna, etc., and has a UART, SPI, or SDIO interface, some type of a serial interface to the module. Okay? It's possible that you want to design your sensor, whatever, we're using an 816-bit, and maybe for you, using these Wi-Fi modules is a solution. Okay? But you need to understand that the interface of the module is over a serial interface. And sometimes it's even like the old modem we used to do, AT, da-da-da-da. Okay, AT, DT, command, you know, do the DTMF, touchtone, etc. So it's an AT command set. Now, if you do this, it means that your application has no knowledge of TCP, of the IP network. You're not opening a socket, you're not closing a socket, you're not sending and transmitting over a socket. That's cool. Also, the module can be fairly expensive. Well, fairly expensive, you know, it depends on your design. But for low volume product design, it would make sense. But there's a grade here in the modules you can use. You can have a module with the radio only, which means that the TCPIP stack and the Wi-Fi stack will run on your main target, on your main board. Okay? For high volume, that's probably preferable. Also, if your system runs Ethernet and Wi-Fi, it's better to have the TCPIP stack on the main target, because this way the TCPIP stack can talk to the Ethernet interface and the Wi-Fi interface as two interfaces from the same TCPIP stack. So your application, open socket, closed socket, etc., will see it the same way. But if you have Ethernet and then a Wi-Fi module that has the TCPIP stack, etc., then your application it will be difficult to design your application, because your application needs to open a socket for Ethernet and send serially to Wi-Fi. This is not normally how you would work with an IP network. You'd like all your interfaces to be from the same stack and let the stack decide which of the interfaces has the best metric, the best performance, etc. Okay? So here, the modules, the pre-manufactured modules with FCC approved, etc., it can be good. You need to do the business case. Look at how many units you're going to manufacture, and look at your software architecture and how you're going to do that. We can say the same thing about Bluetooth. Bluetooth also, you can buy modules with a Bluetooth stack and a Bluetooth radio and interface serially to it. Okay? And this is exactly where we're getting right now. So Bluetooth, there's two flavors of Bluetooth. There's Bluetooth Classic, which is, and you see the size of the stack, you know, of a Bluetooth Classic, and then a Bluetooth Low Energy. Okay, so Bluetooth Low Energy is the latest version, or sometimes referred to as Bluetooth 4.0. Bluetooth 4.0. But you see, the size of the Bluetooth low energy stack is about 200 kilobytes. Again, you know, depending on the memory you have available on your target, that can be a lot of code running on that target. Now, the thing with Bluetooth low energy is that the IETF just drafted and approved a standard to run 6LoWPAN using the Bluetooth radio. Now, Bluetooth Implementer Forum did not approve it yet, but they're in the review process. Now, if you were looking for a wireless local networking technology, and you were looking at Zigbee or Z-Wave or Wireless HART or ISA100, etc., yes, you can look at it. Depending on when you need it, then if you can wait for Bluetooth Implementer Forum to ratify the use of 6LoWPAN over the Bluetooth Low Energy radio, then that would be the solution. Because suddenly, you're going to have IP connectivity from end to end, okay, which the other protocols don't allow you to do. All right? And why the Bluetooth Low Energy? It's because in North America, and I'll get to it here, I think, cellular modem, that's one of them. Here. In North America, the Bluetooth coexists really well with Wi-Fi, okay? In Europe, they don't have the same issue. This is why Zigbee works well in Europe. But in North America, Zigbee and Wi-Fi, they don't work well in the spectrum space. But Bluetooth and Wi-Fi, they work well. Now, if we can have 6LoWPAN over Bluetooth radio, then for us, we have then the close range wireless, the longer range wireless with Wi-Fi, and we have the best of all worlds. Okay. Now, one last interface that is often important for a thing, an embedded device, would be a cellular interface. Okay. And in this case here, it's the same thing. There's many cellular modem vendors that are available. But again, here, if you select one, I strongly suggest you select one that has an interface over a serial interface using point-to-point protocol, PPP. PPP is another of the protocol that ends in P that is part of the TCPIP family. Everything that ends in P is almost part of the same P protocol family, okay? So if you have PPP, it means that if you can have then Ethernet and Wi-Fi and 3G from the same TCPIP stack, interfacing all these networking interfaces, okay? So cellular fleet management, okay? Put it on a car, on a truck, on a whatever. Alarm systems as a backup communication if the thief just went and flipped the telephone line. You know, there's multiple applications here for a cellular networking capability. And this is the wireless LAN. Okay, we're getting so close to the end. I hope I'm not boring you. I'm trying to go fast. I just want to make sure we'll have time for questions later. Okay, in the internet, I told you that there were hundreds of protocols for we humans using the web. You know, HTTP and HTML and XML and SOAP and WebSockets and all kinds of other stuff. For devices, for things, we're also starting to see other protocols being created. Now, does it mean that you can't use HTTP to build a device and send the information or controls over the internet? No, you can. Okay, you absolutely can. The thing is that a packet using an HTTP request, you know, the REST API, the get, the put, the delete, the post command is fairly heavy. This is why there's protocols that are starting to be defined to be able to do something similar as HTTP, but for machines, for devices. Okay, and the one on the right, it's an example from the second one on the list on the left, which is called CoApp. Co for constrained, okay, application protocol. Okay, constrained why? Because normally embedded devices, as you know, I've already showed you multiple times, we don't have the same performance, we don't have the same code space, we don't have the same RAM space as a laptop, as a smartphone, as a tablet, as a PC. So we need to find ways to do the same thing as these, higher-end computers, but to do it in a smaller computer, okay? And this is why the IETF came with the Constrained Application Protocol. It is kind of a binary HTTP. So in HTTP, all the messages are human readable. If you look at HTTP and you decode it, you can read. Okay, it's a URL, it's a unified resource locator or unified resource identifier, and then blah, blah, blah. You can read because it's human readable. Now in CoAP, it's not human readable anymore. It's binary. But it makes these packets 10 times smaller than an HTTP packet. And it's significant in its usage. Okay? This is a table that came up from Mr. Duffy at Cisco, who looked at some of the protocols. Now, another one I want to draw your attention to is MQTT. MQTT is a protocol that was developed by some people and was picked up by IBM and is now under development in the Eclipse organization. Okay, and it's for message queue telemetry transport. Again, and then the big thing I want to show you is the second line messaging, the difference between HTTP CoAP versus MQTT. Okay, so HTTP and CoAP are request response protocol, while MQTT is a publish subscribe. Publish subscribe, what does it mean is that the MQTT device subscribes to a server and then publishes data. And the server also can also, if you subscribe to the MQTT server with a tablet, with a laptop, with a smartphone, the server will also be able to publish the data that will be collected on the server. And from my point of view, I believe that the protocols that will win in the next 5-10 years are HTTP, yes. Maybe it's not the right protocol for us to use as in the thing, but it is because it's there and it's functional. We can do the initial launch of our product with that. The other two ones are CoAP and MQTT, definitively, because they're really targeted at machines talking to machines over the internet. Okay, these are two excellent protocols that I suggest you take a look at. The wireless gateway with a stack of protocols going again to power management, device firmware upgrade, secure. In this thing here, every time I put TCPIP, I also, I don't mention it, but security is always in there. So at the TCPIP level, it's TLS/SSL, secure socket layer, okay, that encrypts the transmission, like HTTPS. When you're doing a web, you're doing a bank transaction, on your laptop, on your smartphone, on your tablet, you're doing it over HTTPS. So a secured connection is done at the socket layer using SSL or TLS, the transport layer security. It is one of the features of the security. You've also read probably many times on the internet, magazines, etc., that one of the big issue with the Internet of Things is security. Yes, okay? But, when the telephone was invented 130 years ago, it was the same thing because it was party line. Everybody could listen on the line and listen what the other guys were saying. Today, with the internet, we are at the beginning of these technologies. And yes, we need to improve the technology to make it even more secure. Secure in the communication, but secure also in the device itself, in the boot, to have a secure boot, to make sure that the software you're booting is the one you're intended to boot and not something that was transmitted by someone else trying to take control of your device. Sorry, and this is why the remote device firmware upgrade is not only important as a remote device firmware, but as a secured remote device. So there's security in the TCPIP stack for the transport, but security has to be also thought in the boot and in the firmware upgrade. Okay, last but not least is the cloud. What services do we have available today? There's no week that goes by without me seeing a new provider coming up with, we're going to be the cloud, we're going to provide the services to all these 50 billion devices around the world. Yes, okay, maybe yes, maybe no. But what is important, and the other thing is that at Micrium, we're giving training, free training. As long as you can pay your travel to Florida and your lodging, etc., we're going to train you on Realtime Kernel, TCPIP Stack, USB devices, etc. And then when we do this training, we sit with the people that come and visit us, at lunchtime or coffee break, and we ask them, you have an IoT strategy? Yes, we have an IoT strategy. What are you doing with your cloud service? We're going to do it ourselves. Ah, you're going to do it yourself. Okay. Why? Well, because we want to make sure that we're going to be alone and nobody will copy us. Okay. Yes, it is a strategy. Not sure it's the right strategy, but a lot of the people we talk to, they want to do their own back-end services. Okay. Now, you can do your own, or you can also lease it from someone else that already has that service. There's tons of providers out there. Now, the thing is that the small companies that pop up every week, I'm not sure they'll be here in 4 to 5 years. Because who's here in the cloud services? Can you name me a few companies that are in the cloud services today? Can you name a few? Amazon, Microsoft, Google, Oracle, Salesforce.com, okay? Just these 5. These 5 will still be there in 10 years. The small ones, not sure, okay? So this is why there are services available out there. So if I think that HTTP, MQTT, and CoAP are the 3 protocols that will remain, if you want to design your own and put your own servers and manage your thing, then do it with these protocols also. Or find a service provider that also supports these protocols, okay? Now, this is the example when you have an industrial devices. So I have a wireless sensor network. I have a gateway in the case it doesn't talk IP, okay? In the consumer world, then we have these devices, and we can have Wi-Fi direct. We can have Ethernet Wi-Fi, the same thing. So what is important on the cloud service is the availability of these things. If you develop your own cloud service, okay, and it's not everybody that has the expertise of putting servers, scaling servers, geography, geolocation, because a server in North America may not be good for Europe, may not be good for Asia, or vice versa. A server in Asia may not be good. You may have to install servers in multiple time zones, depending to make sure, load balancing and all that stuff. It is a science, okay? I'm coming from the embedded space. Okay, I've been doing C programming, almost all my career, etc. This is another technology. It is in the cloud. It is web technologies. It is Linux servers and Oracle databases and all kinds of other technologies. Not everybody has the expertise to be able to do that. But if you need to do that, you need to be. If you select a vendor that offers you, the capability of doing that, then this is the type of the thing you should look. Now, these web servers, these cloud services, they should allow you to have web interfaces so that you can do your dashboards, your controls, or your reporting. You can develop smartphone applications, iOS applications, Android applications, so that you can give it to your customers so that they can look at the data from the devices or control the devices, etc. Okay, and these are all the type of things that you need to watch out for. Okay, so what I wanted to make sure that you understand is that the IoT is not only the thing. It is the local network. It is the internet protocol. It is the cloud services, etc. But the IoT is just a term that is being overused today. Okay, I don't know. I've been around the electronic and software industry, for more than 30 years now, and there are certain terms like that. When they're overused, they lose their meaning, right? And I'm just afraid that that's what's going to happen to IoT. We're going to use it to so many different sauces, so many different applications, that it's going to lose its meaning. Fine. It's not important. What is important is that we can build devices that are connected, that will bring value to ourselves, the company, and the whole society. The only thing I didn't mention about the cloud services, etc., it's also the availability, the capability of sharing the data or merging the data together. You merge weather data with grid grid cost for kilowatts for electricity. You merge it with something else, and then suddenly you can do things we didn't think would be possible in the past. Okay, so this is why also building silos may not be the right idea. As long as we take IP and we build these things using IP technology, and then so that we leave the door open. We can keep the door closed. It's okay if commercially, financially, we think it's the right thing to do to build our own service and our own cloud. It's fine, but leave the door open in case that we need to do that. So big data, the capability of to do analytics, to do more with the data. We had the discussion at lunch, Chuck and I, and Peter Diamandis, the guy who did the X Prize, who gave the prize to Virgin, who did the first suborbital, go into space, etc. Now he has a new project with Qualcomm. Okay, Qualcomm has also sponsored a contest where people are going to develop a smartphone-sized medical device. That medical device will be able to do urine analysis, blood analysis, take your temperature, take the blood pressure, etc. So you'll be able to do your vitals on a regular basis and build the data. So imagine if all the population of the United States, we take all this data, then imagine if we use it only for ourselves, already it's an advantage because our physician will be able to see, if our blood glucose is ramping up or if we're developing some type of thing. But imagine if we take the value of all the citizens in the United States and we can detect, an epidemic somewhere or some type of things by sharing the data together. This is just an example of the type of things we could do. I'd like to stop here and thank you for the invitation. I'm going to be available now if you have questions to answer questions, and it doesn't have to be questions on the material that I presented to you. It can be on the industry in general, and I'll be more than happy. If you ever want to send me an email, ask me a question. So first name dot last name at micrium.com, and that's how you're going to be able to reach me. I thank you for the invitation. It was a pleasure to be here tonight. And so if you have questions, I'm open. So anything? Yes. Just want to.
I'm Larry Cox, and so you know who I'm talking. My overall interest in technology is, I guess you could say, its impact on a person's life and people's life in general. And we can't go into that deeply here, but a couple of thoughts I had as in terms of the vision that's coming through. It comes kind of like from the technical capabilities of our hardware and software. It's like growing almost exponentially.
Yep.
Is this machine-to-machine communication one thing? That means that one machine can somehow decide that it needs to know something from another machine and tell it that. So that's one whole thing that's kind of like new and different. Be interested in if you have any like ideas of where that's going, and also just the general concern people have of sort of the invasiveness of this technology, and how am I going to still be able to run my own life, or is my smartphone going to run my life for me? And like, can I turn it off? Stuff like that.
See, I cannot answer the question for the people who are going to develop the systems, okay? Because I'm working with all kinds of companies that have all kinds of ideas, okay? And some ideas are just commercial ideas, okay? I know an alarm company that wants to have an interface to Facebook so that they can load the picture on the alarm system control panel. It's a gizmo, okay? But other companies want to, for example, save energy. So how to turn on and off certain appliances depending on the cost of electricity or gas today, tomorrow, tonight, etc. So there's one that are useful and one that are not. Now, as humans, we always have the free will to turn on or off things, okay? And I think we have to exercise our own judgment. If you don't want it, okay. And there's an example right now in Montreal, where I'm coming from. The Hydro-Quebec, the electric utility, is now changing all the meters and putting meters with a wireless communication device, okay? And all the people say, I don't want it, okay? And they're entitled. They can refuse the installation of this new meter. Okay, so they're going to pay for someone to roll out and read the meter once a month. It's their choice, but you can say no. Okay, so there's always pros and cons to do. You want it or you don't want it. You know, yes, I agree with you. You know, Android smartphones, wonderful. If you want it, you buy one. If you don't want it, you don't buy it. But that's why. Okay, and then if you want it, there's all kinds of features on it. You can turn on and off, and you know. So the thing is that maybe it's Edward Snowden and all these revelations. So are we afraid that this information will be used against our will? We have to be like good citizens and look for it, because I don't think we can trust anybody now with all these revelations about NSA and what they've been doing with phone and spying and all that stuff. I agree with you, but as good citizens, I think we have to be alert and look at what's going on. But there's tons of potentials in what we can do into improving energy, environmental safe devices that will improve our lives. So I'm an optimist. So I'm always looking at the right side, the good side of things. I have a friend that is a pessimist and has always said, we should start a pessimist club, and finally said, won't work. Other questions? Thank you very much for your time. It was a pleasure to be here today and with you, and I hope you learned anything. And of course, in the time we had, there's a lot more than. So that's why, if you have other questions on clouds, on what people are doing, on the hardware, on the software, on the things. But what I want to make sure you get is that IoT is not one thing. IoT is what you're going to make out of it. Okay, so don't try to find a unique definition. We have to make the definition ourselves by being creative, innovative in the products and services we're going to develop and make available to our customers, our relatives, our friends, our family, our colleagues, citizens in the world. IoT is what we're going to make out of it. It's not what people tell you what it is. All right? Thank you.